In the last lecture, we looked at repetition code and saw that it doesn't allow us to send a positive number of bits per channel use. And we asked the question: is there a better code that can send positive number of bits per channel use as the error vanishes? Okay, and this is precisely what channel capacity is. It is defined as the maximum number of bits that one can send per channel use as probability of error vanishes. So let us formulate this problem more carefully. Let us start with the definition of a channel code. So a channel code of length n and size m is given by a pair of mappings. The mapping E and the mapping D, where the mapping E is the encoder mapping and D is the decoder mapping. So mapping E is a mapping from the messages to the input of the channel, the code words, n length code words. This n and this n are the same, and the number of messages is m. Okay. So this is the encoder mapping, being the encoder mapping. And the mapping D looks at what has been received. So yn, remember the channel W that we are looking at has input alphabet X and output alphabet Y. So we look at what we receive out the channel output and declare a message. Sometimes we also allow an additional bot symbol here when we want the decoder to also detect an error, but we are not allowing that in our formulation. Being the decoder. Okay. So these are the two mappings which define a code. The probability of error for this code is given by one by m summation m equal to 1 to m. So the average probability of error, probability that the decoder looks at the channel output and that is not equal to m, given that m is sent. Okay. So this guy here, this yn, this is the channel output. Okay. So we can expand this expression further. This is exactly equal to 1 by m summation over m summation over all the received vectors y such that d of y is not equal to m. Wn of y given e of m. Okay, that's what probability of error is. And this particular notion of probability of error here this guy here, okay, which is equal to this guy here. This notion is the average probability of error. So it's the average probability of error averaged over the messages. And we can look at a more stringent notion of probability of error, namely the maximum probability of error. But for now, let's start with the average probability of error. Okay. So we now know what the probability of error for a code is. Now the other thing that we need for a code uh, is its rate. The rate of code comma d above is given by, so rate is just the number of messages that the code sends per channel use, log m by n. Okay. So this rate, when you look at some standard like Wi-Fi or LTE, it talks about the MCS, the modulation and coding scheme, and that is described by two things: the modulation scheme used, which can be something like a 64 com or a 16 com, and the rate of the code used, which will be something like half. That rate refers to this ratio. The code that you're using, what is the number of message bits it sends per channel use. Okay. So we are interested in maximizing this rate. Okay. Uh, Rate of the code. Let's bring in another notation. Denote by m of n comma epsilon the minimum size, the maximum size of a code of length n and average probability of error less than equal to epsilon. Okay, it's maximum because it's just a number. I'm defining this m to be an integer, so you can just take a look at all the integer, and at some point you cannot attain this small probability of error using just the channel n times, and that's the maximum is given by that, just one before that point. Okay. All right. So now we have defined what a channel code is we have defined its, so it has an encoder and a decoder. We have defined its rate. We have defined its average probability of error, and we have introduced this notation m n epsilon, the maximum number of messages that you can send with probability of error less than epsilon using the channel n times. Okay. The next definition using this that we have is that of an achievable rate. In fact, we'll directly define channel capacity. So another definition. This is the notion of channel capacity. Okay. Channel code, and this is channel capacity. So before we define channel capacity, we define what is called an achievable rate. A rate r greater than 0 is an epsilon achievable rate. If if you can find, or if there exists, okay, we already have this notation, if the maximum number of messages that you can send with n channel users with probability of error less than epsilon exceeds 2 to the power nr. That is, you can send more than nr bits of messages, and you only need to do this for all n sufficiently large. So this is sort of an asymptotic quantity. So denote by c epsilon w the supremum over all achievable rates. By the way, I've used the phrase supremum here. It is, as I've mentioned several times before in the course, this is like maximum, but slightly more formal notion defined by limits. You can look it up if you don't know what it means. Overall achievable rates, denoted by C epsilon W, the supremum overall achievable rates. The capacity of a channel W, this is the main definition we want to define, capacity of a channel, is given by CW. Now, if you look at the C epsilon W, this is roughly the maximum rate at which you can send with probability of error less than epsilon by using codes of longer and longer length, because we only want it for all and sufficiently large. And this C epsilon W is an increasing function of epsilon. As epsilon increases, this will also increase. So when you say so you can take this limit because it's just a monotone function, and this corresponds to the rate at which you can send with vanishing error, and that's what capacity is, the rate at which you can send with vanishing error. Okay, that's what channel capacity is. So this is just a rough thing because limits may not, this limit exists, but roughly speaking, the CW is limit epsilon going to 0, limit n going to infinity, 1 by n log of mn epsilon. Okay, so this is a rough thing because I've not told you that this limit exists. Turns out that this limit exists, but without having that theorem, it's not clear if we can write it this way. But yeah, that's what we are saying. Formally, if you do it, you will define it using lim sup or lim infer. Okay, that's what channel capacity is. So one of the most fundamental theorem in information theory is this result called Shannon's channel coding theorem. Okay, and what it says is it gives a characterization of this channel capacity for a channel W from X to Y. So for now, we only have discrete input and output alphabet in our mind, but this result holds for much more general channels with X and Y discrete. The channel capacity CW, which is defined this way, is given by, this is a formula, this is an answer we are giving. Sometimes this formula is treated as a definition of channel capacity. This is an answer, it's not the operational question. The operational question is above here. So this is given by max over all input distribution, the mutual information between the input distribution and W. Okay, that's what channel capacity is. This is perhaps the most important formula in Shannon theory. Okay, so CW is max over all input distribution, the mutual information of Ix and W. So in simple words, this is max over all input distribution, the mutual information between the input X and the output Y, where X and Y are passed to the same channel W. But this notation is more convenient. So why can we take this max? Well, firstly, this would have been a sup, except that we are taking sup over these distributions, and this is a nice continuous function for discrete case, and therefore it becomes max. Also, note that IPW is a concave function of P, and therefore there'll be, it's not strictly concave, but it's a concave function, and therefore even this is a convex function and we are maximizing. This is a concave function and we are maximizing it. So this is the theorem. We haven't proved it, and we'll spend the next few lectures proving it. But in this lecture, I wanted to state the theorem. That's Shannon's channel capacity theorem, channel coding theorem. Earlier, we saw Shannon's source coding theorem, where we had characterized the minimum asymptotic length of a source code, and that was entropy. And note that if the channel is a perfect channel, namely y equals to x, then mutual information is exactly equal to entropy. Okay, but here it's a slightly different problem where we get to define this px. Okay. So now, before we prove it, let's look at some examples for computing this channel capacity. And what we will introduce is something called duality bounds. Okay. So I'll recall a formula which we saw earlier. We saw that this channel capacity, which is max over px I px of w, is also equal to so-called information radius, minimum over all output distribution, maximum over all x divergence between px and q. So the way to visualize this formula is that for each x, you have an output distribution wx. So we take a q, another output distribution, look at the divergence of each of them from this, and look for a q which minimizes this. So this min-max minimizes the maximum distance. This min-max is akin to a radius, and this is called the information radius of this channel w, or for this channel w. And this size, of course, is the formula for capacity. This result basically says that capacity equals to the information radius. Okay. In particular, these two results together give a nice bound on capacity from both sides. So what we know is that channel capacity must exceed IPXW and must be less than max over x d wx cube. Okay, this must hold. It must hold all the time. So for all input distributions px and output distribution q. So what do I mean by the way, this q is in the probability simplex on the output alphabet. Okay, so this bound always holds. So by using any input distribution, we'll get a lower bound for px, and by using any output distribution, we'll get an upper bound for we'll get a lower bound for cw, and by using any output distribution, we'll get an upper bound for cw. Alright, so let's now take a look at our favorite examples of binary symmetric channel and binary erasure channel, and look at what cw evaluates for those guys. So we are assuming currently Shannon's channel coding theorem. We'll prove it in the next class. So now if you have a BSC with probability of error delta, then CW. So we use PX equals to uniform 0, 1. For this input distribution, the mutual information between input x and output y equals to entropy of y minus the entropy of y given x. Note that for each x, for binary symmetric channel, the output has the same distribution. So the output entropy, not the same distribution, the output has the same entropy. It's the binary entropy of delta. Also, when x is uniform, there's something to check. The distribution of y is py0 with probability of half x is 1, and when it's 1 you can see 0 with probability 1 minus delta, and the probability of half x is 0. Probability of with probability half x is 0, and then you see 0 with probability 1 minus delta, and probability of half x is 1, and then you see 0 with probability delta, and overall if it's half. So this is half, and therefore y is uniform, so this is just 1 minus h of delta. Okay, so if you look at this duality bound, this guy implies CW must exceed 1 minus h of delta. So we got one bound. For the other side, we now have to tell you an output distribution. So again, we'll use just a uniform distribution. That's what we use. And we look at this max of the two divergence between W0 and uniform, and divergence between W1 and uniform. This is equal to max of, so what is the divergence between W0 and uniform? That's delta, actually you can check this, that's exactly 1 minus h delta, and this is also exactly 1 minus h delta. Okay, so this max is just 1 minus h delta. Therefore, again by duality bound, this CW must also be less than equal to 1 minus h delta. Sorry, this, yeah. Okay, yeah. So because we have an output distribution, so this is less than this. I was a bit fast here, but you can confirm this. For uniform, the divergence between any distribution and uniform is log of cardinality of alphabet minus the entropy of the distribution. So in this case, the alphabet is binary, so it's just 1. Okay, so we have both bounds. So if you combine this bound 1 and bound 2, CW for the binary symmetric channel is exactly equal to 1 minus h delta. Okay, so 1 minus h delta, that's the capacity of the binary symmetric channel. So if you want to draw it as a function of delta, we know this, right? So at delta equal to 0, this is 1, and at delta equal to half, this is 0. Okay, we just need to consider delta up to half. After half, you can essentially flip 0 and 1 at the receiver. Next, we go to the binary erasure channel. Okay, so we look at this BEC delta. Okay, so once again we'll use the same idea. We'll use the input distribution Px, we'll use the uniform distribution. By the way, you may ask why I'm using a uniform distribution. Here it is clear. It's not an arbitrary guess. In this case, the second term always remains h delta, no matter what the input distribution is, because of symmetry. And right, so that's just h delta. And so we want to find an input distribution which maximizes the entropy of y. And since the maximum is 1, maximum can at most be 1, and which is attained by uniform distribution at the input, I chose the maximizing distribution, which is the uniform distribution. Okay, once again, if I use this guy here, then the mutual information between x and y is h of y minus h of y given delta, y given x. Now, what is the entropy of y given x? This is h of y minus, yeah. So when x is 0, y will take probability 0 with y will take the value 0 with probability delta, with probability of minus delta, and erasure with probability delta, and similarly for x equal to 1. So this becomes h delta. How about h of y? Now y can take three values. What is the probability that y takes the value 0? That probability is half into 1 minus delta, log of 2 by 1 minus delta. What's the probability with which you'll take y will take the value 1? That probability is half into 1 minus delta. Okay, log of 2 by 1 minus delta. What's the probability that y will take the value erasure? That probability is half plus half delta. So that's just delta. So that's delta log 1 by delta minus h delta. So this becomes so overall this becomes 1 minus delta plus the first term is entropy of delta minus entropy of delta. So you will check that this has become 1 minus delta. So what we therefore get is, from this calculation, what we get is CW must be more than 1 minus delta. Now again, using Q equals to, now I use the same output distribution. That's just a guess to see what happens. It doesn't work all the time, but sometimes it works. Okay. So this is the output distribution corresponding to the input I've used here. This distribution has divergence of W0 from Q given by, so under 0 the output distribution just takes the value 0 with probability 1 minus delta. This one takes the value 0 with probability 1 minus delta by 2. This one takes the value erasure with probability 0, 1 erasure with probability delta log delta, and this is also delta, and it never takes the value under W0. You never take the value 1, so there's nothing here. So this is just 0, and so if you write it, you just get 1 minus delta. Okay, and similarly divergence between W1 and Q is also 1 minus delta. Okay. Therefore CW must also be less than 1 minus delta. That's the second bound. So now if you combine these two bounds, let's call them 3, 4. CW for erasure channel is exactly 1 minus delta. Okay, so this completes a second example. We have found that the capacity for the binary symmetric channel is 1 minus h delta, and for the binary erasure channel is 1 minus delta. And throughout we were using this duality bounds, which are very handy and can be used to find very useful bounds for capacity, which are tight, sometimes tight. And in general, we were relying on this theorem called Shannon's channel capacity theorem, which we haven't proved yet, but that's what we will prove in the next class, starting with the binary symmetric channel and then going to the general channel. That's the agenda for the next class. In fact, this is the end of this unit, where I just wanted to define repetition code, motivate channel capacity, and then bring out this duality bounds. In the next class, we will prove Shannon's, in the next unit, We'll prove Shannon's channel coding theorem, first for binary symmetric channel and then for a general channel. See you in the next lecture.